In this video, I want to continue looking at the exponent rules for groups. Our author has described the exponent rules in this particular theorem, and I asked you to copy it down in the last video. It's important to realize that the first two properties are the familiar rules from regular old arithmetic, and it's important that this third property is a little bit weird, and more importantly, it's important to understand that the familiar third property only works if G is an abelian group. In other words, GH raised to the n is equal to G to the n times H to the n only when G is an abelian group. In the previous video, we proved this lemma, that if G is a group and we take any element in G and K is a positive integer, then the expression G to the minus K can denote either one of these particular things, because the inverse of G to the K is G inverse raised to the K, and we can denote both of those by G to the minus K. So what I now want to do is I want to look at proving the first property of theorem 3.23. So let me get that back, and let's see. So, oops, wrong color. I want to prove that G to the m times G to the n is equal to G to the m plus n in a group. And let's get rid of that stray mark. Now, I'm going to break this into three main cases. The first case is the easiest case. M and n are both at least as big as 0. And then just the meaning of what a basic exponent with a positive integer means is all that we need here. G to the m times G to the n is going to be a bunch of g's multiplied together, and we are going to have m copies of G there, and then we have another bunch of G's multiplied together here, and here we have n copies of G, and when we add them together, we have a total of m plus n copies of G. So in the first case, everything is easy. Well, let's look at the second case. Case 2, n and n are both going to be less than or equal to 0. Now, to make it clear what's going on, I am going to let m be equal to -1 times L for a positive integer L, and I am going to let n be equal to -1 times K for a positive integer named K. In other words, L is equal to minus m and K is equal to minus n, and it just helps me by knowing that I've got positive integers without having to think in terms of, oh, there's a minus sign, but that minus sign is really positive. So now let's look at what the expression G to the m times G to the n actually means. Well, G to the m is G to the minus L, and G to the n is G to the minus K. But now I know how to deal with both of these since K and L are positive. The first one is going to be G to the -1 raised to the L, and this one is going to be G to the -1 raised to the K. And so what we have now is G to the -1 all the way up to G to the -1, and we've got L copies of G to the -1, and over here we've got G to the -1 all the way up to the last one of them, and we have K copies of G to the -1 over here. So we clearly have G to the -1 raised to the L plus K. But I know by that previous lemma how to deal with this. So we use the lemma here. And we're using the lemma again here to rewrite this as g to the minus L plus k. But g to the minus L plus k is g to the minus L plus minus k, and that will now be g to the m plus n. And I've got a stray mark there, and I do want to say why here. This is because minus L minus k is nothing more than m plus n, since minus L is equal to m and minus k is equal to n. So now we have to deal with the last case, and the last case is when m and n have different plus minus signs. So it breaks down into two subcases, and I'll actually call each one of those subcases its own case. Our third case is going to be m is bigger than or equal to 0, and n will be less than or equal to 0. Now, just like before, I am going to choose to write that negative n as negative 1 times k, where k is positive. Pardon me. And when I do that, we see that g to the m times g to the n becomes g to the m times g to the minus k, but I know how to deal with minus k. This will be g to the m times g inverse to the k, and k is positive. So what I've got now is g times g all the way up to g, where I've got m copies of g. And then I've got g inverse times g inverse all the way up to g inverse, and I have k copies of g inverse. Now, what happens to this is going to depend upon whether or not m or k is bigger. So let me think about breaking that down into two subcases. If m is bigger than k, then when we start looking at this, we can cancel each one of these g inverses with a g, and we finally get down to the last one, and we have leftover g's. And the number of leftover g's that we have is going to be m minus k, the number of them that got canceled off. And so I'm going to write g to the m times g to the n will wind up being g to the m minus k, which is the number of leftover g's after we do all this canceling. But what I want to notice is that g to the m minus k is going to be g to the m plus minus k, and remember, n is equal to minus k, so this expression here boils down to g to the m plus n, and that is because we are looking at m plus minus k. Well, what happens if m is smaller than k? So let's look at that. If m is smaller than k, when we've got this expression here, and we have m copies of g, and we have k copies of g inverse, The canceling this time is going to actually, I need to undo that. The canceling this time is going to go like this until we finally get rid of the last one of those. And we're going to have leftover G inverses. And the number of leftover G inverses is going to be the total number of them, which was K, minus all of the ones that get canceled by having a corresponding G. So we're going to have K minus M leftovers. So in this case, G to the M times G to the N is going to wind up being G inverse to the K minus M. Now, by that lemma, our lemma kicks in again, we can rewrite this as G to the negative 1 times K minus M, which is G to the minus K plus M, which is G to the M minus K, and that is G to the M plus N, and this last is true since minus K is simply another name for N. And so that gets us this third case. The fourth case is very similar to the third case, and all I'm going to say here is that the fourth case, when M is the one that's less than or equal to 0, and N is the one that is bigger than or equal to 0, is basically the same kind of case as case 3. And I'm going to actually leave that for a quickly jot and class assignment.